Or perhaps the river of time can have whirlpools and time can go in on itself. In that case, time travel is something you have to take very seriously.
Michio Kaku shocked everyone when he suggested that time might not be as we perceive it, all thanks to a revelation from the James Webb Telescope. According to the renowned physicist, this groundbreaking discovery challenges our conventional understanding of time. But how exactly did the JWST uncover such a revelation? Join us as we delve into the intriguing question of whether time truly exists, as proposed by Michio Kaku, with insights from the James Webb Telescope. The Big Bang didn't happen. Launched on Christmas Day 2021, the James Webb Space Telescope, or JWST, is essentially the Hubble Space Telescope's bigger, cooler brother. It has made its home in orbit, illuminating secrets from the universe's darkest and most remote corners. With its extremely potent infrared instruments, it resembles the ultimate time machine and is ideal for looking back in time. Thanks to its unparalleled sensitivity and resolution, it can identify extremely faint and old objects that even Hubble was unable to see. We're talking about far-off galaxies and celestial bodies from the early universe, those elusive entities that have, in essence, been playing a grand game of cosmic hide-and-seek with us. One infrared picture at a time, James Webb is assisting us in assembling the grand star-studded jigsaw puzzle of the universe. Imagine being at an art gallery and browsing through magnificent images taken by the James Webb Space Telescope. The imagery is amazing, showing far-off galaxies shimmering across the cosmic canvas. But among the astronomers and cosmologists, you notice shock and disbelief. There's a sense of turmoil that makes it seem as though they're staring at a Van Gogh in a room full of realists. The frequent response is, "This is unexpected," referring to how their entire conception of the universe has been rocked. The Big Bang Theory, which holds that our universe began with a massive explosion some 14 billion years ago and has been expanding like a giant balloon ever since, is the real issue, even though official papers are tight-lipped. This theory has been the cornerstone of cosmological understanding for years, but the new images from the JWST seem to be challenging its validity, sending shockwaves through the community. These images depict galaxies appearing smaller than we'd expect, even those that shine brighter and pack more mass than in our own Milky Way. It's as though you're expecting your faraway friends to appear as tiny dots on the horizon, but instead, they're right next to you, just as large as life. These images appear to reveal galaxies that are 2 to 3 times smaller than those observed with the Hubble Space Telescope, or HST. These galaxies have considerably higher redshifts, which, to put it simply, indicates they are purportedly traveling away from us at quicker rates, in addition to having greater luminosity and mass. It is a strange observation, especially if you believe that the universe is always expanding. It was expected that the JWST would continue this trend, and it did, even for galaxies with redshifts as high as 12 after some scientists first noticed this discrepancy back in 2014. They analyzed HST images and found that galaxies with redshifts up to 5 seemed to match what you'd expect in a non-expanding typical space. If we continue to believe in the Big Bang Theory and its expanding universe theory, we are left with a rather perplexing conclusion. These distant galaxies must be incredibly small to counterbalance the supposed optical illusion created by an expanding universe. It is a bit like imagining a grain of sand with the brightness of a spotlight. To put it another way, the JWST images show galaxies that appear the same as those close to us, as if the universe isn't expanding. When you consider these tiny and smooth galaxies, the idea of an expanding universe, and, by extension, the Big Bang Theory, starts to crumble. Take, for example, the galaxy named GZ2, which the JWST spotted, is far brighter than the Milky Way but is calculated to be only 300 light-years in radius, compared to the Milky Way's 50,000 light-year radius. Not only that, but its brightness per unit area would be 600 times that of the brightest galaxy in our local universe. Also, its density, and that of several other new galaxies, would be tens of thousands of times higher than the galaxies we see around us today. They have struggled throughout the years with the photographs from the Hubble Space Telescope, which appear to show the existence of numerous galaxies that are powerful and dense, akin to Mighty Mouse from classic cartoons. They find these galaxies to be a difficult conundrum, and understanding these unusually small galaxies has only grown more difficult with the advent of the James Webb Space Telescope. The idea proposed by theorists is that these microgalaxies smash into each other over billions of years to form the full-sized galaxies we see today. It's like playing with a magical tiny toy car that weighs as much as an actual SUV. Here's the twist, though. The JWST has closely examined these galaxies and discovered no evidence of these cosmic collisions. One might think that these colliding galaxies would exhibit some damage, perhaps appearing a little jumbled or twisted like a car after a collision. But what the JWST finds instead are smooth, orderly, spiral galaxies that resemble the ones we see nearby. According to a research fittingly named Panic, there are 10 times more of these perfect spiral galaxies than theorists had anticipated. This is comparable to discovering a busy freeway with moving automobiles, but no accidents. The idea that these tiny galaxies somehow expanded into their larger counterparts falls apart if they didn't grow in size, which implies they weren't small to begin with. Without this illusion, the optical illusion we'd expect from an expanding universe doesn't seem to be there, and the concept of expansion loses ground, which is why Big Bang enthusiasts are becoming increasingly uneasy. This is a pretty significant blow to the collision theory. Using the James Webb Space Telescope, scientists like Michio Kaku have been able to find out so much about the universe, even up to its age. How old is the universe? According to Michio Kaku, who was able to look billions of years into the cosmos and take pictures that illuminated the universe's beginnings, this amazing instrument, rather than taking pictures in our familiar visual spectrum, is focused on the infrared, exposing colors of galaxies so far away we could never detect them with the naked eye. A fascinating part of this is that not only are these colors stunning, but they also provide information on how old the stars are in these galaxies. Young, hot stars shine brightly blue, while older, cooler stars that resemble our sun glow in hues of red and yellow. Astronomers can determine the age of the star populations in these far-off galaxies by analyzing their colors. Following the Big Bang theory, the galaxies in the JWST photos that are the furthest apart represent a cosmic snapshot taken approximately 400 to 500 million years after the universe's creation. However, some of these galaxies seem to contain stars that are more than 1 billion years old. It appears that galaxies as massive as the Milky Way were already fairly common even a few hundred million years before the supposed Big Bang. If you've been following the Big Bang theory, you know that's a big problem because nothing should be older than the Big Bang itself. Another expectation, if the Big Bang theory is correct, is that as we gaze farther into space, which means looking further back in time, we should see fewer and fewer galaxies until we reach a point where there are none, a cosmic dark age, if you will. The question then is, how so many large galaxies could have formed in such a short time? The answer is probably that they couldn't, at least not within the constraints of the Big Bang theory. For this reason, these discoveries are upending the basis of our understanding of the universe. The new images show that there are at least 100,000 times more galaxies than predicted at high redshifts of more than 10. Additionally, there is this fascinating piece of information that raises the possibility that the Big Bang theory is inaccurate in some ways. The quantity of deuterium, which is simply a fancy word for a form of hydrogen, is the single forecast that the Big Bang theory nails, according to recent research, which is surprising because it indicates that the theory gets 16 predictions incorrect. But the problems don't end there. This theory, which we have adhered to for years, has been forecasting that the universe will have twice as much helium and 20 times as much lithium as we do. Furthermore, the Big Bang theory falters when attempting to explain the massive structures we observe in the universe, because they are simply too large to have formed in the time since the universe's inception. Lastly, there's this interesting fact to consider. Remember those supposedly non-existent asymmetry in the cosmic microwave background? Well, it turns out that they do exist. It's like a cosmic plot twist. So where does this leave us? The James Webb Space Telescope is our answer. These inconsistencies may appear like small details in the vast panorama of cosmic knowledge we have accumulated, but we can assure you they are far from insignificant. Each minor error is like a missing piece in our cosmic jigsaw puzzle. It obstructs the big picture, leaving us with an incomplete understanding of the universe's nature and origins. Not to mention, these aren't just any random puzzle pieces. This technological wonder may hold the answers to these cosmic contradictions. These anomalies challenge our understanding of cosmic structures, the very fabric of space-time, and everything we thought we knew about the formation and evolution of the cosmos. These insights have a profound impact on our understanding of dark matter, gravitational waves, universal expansion, and even the ultimate fate of the universe. They are cornerstones of our understanding of space and matter. The unexpected asymmetries in the cosmic microwave background, for example, could affect our knowledge of the universe's initial conditions and its rate of expansion. To make matters worse, these inconsistencies even have implications for our understanding of time itself, since our current understanding of time is linked to the evolution of the universe since the Big Bang. For example, if the density of matter is off, it could change our understanding of how galaxies form and evolve, as well as our perspective on dark matter's role in it. With all the contradictions we have seen since the JWST, we may need to reevaluate how we understand time, its flow, and its relationship to space if the Big Bang theory is proven to be false. Is time merely an illusion? Have you ever wondered if time as we know it exists, or if it is just a concept created by humans to help us separate the past from the present? This may seem like a strange question, but bear with us. There is a theory that contends that time is an illusion created from our human memories, and that everything that has ever happened or will happen is happening right now. Now let's investigate this more. You might assume that time flows forward naturally, but as it turns out, the laws of physics do not require that time move forward or backward. If you've heard of the Big Crunch theory, it suggests that time may start to run backward when the universe finishes expanding, and that as the universe shrinks, it will get hotter, sort of like a Big Bang in reverse. You might be wondering what comes after the Big Crunch, and that's a question that has perplexed us all. Some ideas propose that a new Big Bang could create a new cosmos. There are even hypotheses proposing that this cycle might repeat itself repeatedly, creating an infinite number of universes, while some argue that our world might reappear somewhere else, totally like a cosmic bubble popping into existence. Given the peculiar potential for time to move either forward or backward, some scientists have boldly concluded that time is merely a human fabrication. They contend that space and time are interwoven in the block universe in which we exist, a view backed by Einstein's theory of relativity. According to this theory, every event in the past, present, and future has a unique coordinate in the four-dimensional space-time. What does that mean for us? It implies that everything exists somewhere in space-time, and that everything is as real as the here and now. This idea was eloquently stated by Swedish-American MIT physicist Max Tegmark, who argued that we may think of our world as a four-dimensional space in which nothing happens or everything just is. If the latter is the case, then time is an illusion since nothing changes. Past, present, and future are all eternal. These are difficult concepts to comprehend, but it's fascinating to consider them because they highlight how incredibly magical and mysterious our universe is. Then there is Julian Barbour, a British physicist with an interesting take on time. According to Barbour, the universe is essentially made up of a series of discrete now moments, similar to individual snapshots. To put it another way, Barbour compares our reality to flipping through a photo album, where each image is distinct now. Barbour contends that our memories of the past are a construct of our perception of it. In other words, We only feel as though we have a history because we have recollections of it. According to Barber, the idea of the past itself may be an illusion. He expands on this idea in his theory of space, which holds that every moment of the present exists in a location within a vast landscape that he jokingly refers to as Plutonia. Each point in Plutonia represents a now, and the landscape itself is perfectly composed of mathematical rules, making it this timeless viewpoint that has a connection to a far more well-known person, Albert Einstein. Although Einstein's theory of space-time is essential to our current knowledge of the cosmos, several important questions have arisen concerning its ramifications and our perception of it. What if Einstein's theory of space-time was incorrect? Would we still be able to understand the cosmos better if we rejected it completely? To better understand how time works, let's further investigate the concept of time. Unraveling time through the block universe. Think of the universe as something being drawn on paper. Every image captures the entirety of the universe's activity in a single instant. Every second brings forth a new set of events. People are born, pass on, civilizations across galaxies grow, and a new drawing is made to replace the previous one. The past is the past. The future has not yet been drawn and is still to come. Every instant is being replaced by the subsequent one. The past is long gone, and there is no future. However, what if time isn't just one thing? What happens if all the drawings are completed and arranged in a towering manner instead of side by side? In this manner, the entire history of the universe is contained in a block of time. Every moment that has ever existed and every moment that will exist. However, the past, present, and future are all equally real and present in this block and stack of moments. But how are the past and future real at this moment if they are all happening in a stack? The issue is that they sort of have to be following relativity theory. Relativity, to put it very simply, holds that space and time are one continuous space-time rather than two distinct entities. You are going through time as well as through space. This implies that the way individuals move through space in relation to one another affects how time passes for each individual. Furthermore, this implies that a person's perception of the present is a certain cut along the block, depending on how quickly they are going. As a result, the present you perceive to be universal is just your own. There are several equally real presents around the world. Therefore, neither the past nor the future are universal. The fundamental tenet of relativity is cosmic democracy, which holds that every observer's perspective is equally legitimate throughout the cosmos. Each of those present needs to be just as real. However, if this is the case, then your past, present, and future must all exist simultaneously. This implies that there is no real difference between the past, present, and future. The universe is a static block in which the past, present, and future all coexist and are real, rather than a collection of things changing over time like in a movie. Consider a galaxy that is too far away to ever go to or observe, that is one outside the observable universe. Whether or not you are unable to visit and see it, it is still real. But if the future is happening right now, how do we make sense of the ability to make choices that determine the future? Is the future already decided? The future must already be written if all times coexist and are equally real. The way we experience the world makes us think that the choices we make will shape our destiny. In our perception, we have the freedom to decide whether to do something or not. However, if the future is predetermined, it means we are unable to decide anything. Are our decisions therefore a mirage? Perhaps we are not really free. It is simply hard to say for sure. However, quantum materials are destroying everything we know. Not even in theory can one predict a quantum process, and it's not because we're stupid and don't know how to accomplish it. Quantum particles are inherently random, according to quantum physics. An atom that is radioactive, for instance, could decay right now, in the next second, or 1,000,000 years. We can calculate the likelihood that something will decay, but no oracle in the universe will ever be able to tell you for sure if it will decay or not. The world can be altered by quantum particles. Imagine that a nearby mammal experiences a genetic mutation as a result of a radioactive material that decays at random. And after many generations, that mutation produced an odd hybrid of a mammal and a duck that defies logic, or the strange creature vanishes a day after the atom decays. The future is not definite if quantum mechanics are truly unpredictable. However, the future cannot be real in the same sense as the past if it is an untold story. What transpires then when improbable events, such as the atom's destruction, come to pass? Is that the current moment? Is this the present? Before quantum materials, we understood that cosmic democracy prevents the definition of an absolute present. It turns out that the past, present, and future are always clearly defined for every single object, including you. Your end will never occur before or simultaneously with your birth. It will always occur after. You are obviously between your birth and your end right now. Thus, the present makes perfect sense, at least for you. When we stop playing tricks, like traveling to the other side of the universe and using advanced technology like the James Webb Space Telescope to figure out what the present means, things begin to appear beautiful and orderly once more, and distinct presents appear to exist. Now let's go back to the world of blocks. Perhaps the future is not contained in the block, or perhaps our perception of it was incorrect. Perhaps a thin coating on the surface represents the current, and the block represents only the past. That surface is uneven and lumpy rather than smooth. It was created by combining innumerable distinct presents, each of which was experienced by someone or something in the cosmos and was legitimate and real in its own right. Furthermore, as each spectator contributes in some way, cosmic democracy endures. Perhaps, as new things occur, the border of this block advances upward, generating fresh time in the cosmos, and uncertain things turn certain. Rather than being a fixed block of time with a predetermined future, the block is expanding as events take place. In such a case, you are once more in charge of your destiny. But it remains true that the only constant thing is change. And that's even truer with science. Science is never static. This may sound shocking, but it's crucial to realize that science depends on these kinds of revolutions. Theories are always being tested, improved, and occasionally completely replaced, and science advances because of this never-ending cycle of research and discovery. A historical examination would demonstrate how this process has developed over time. For more than a millennium, the geocentric model, which held that Earth is the center of the solar system, was widely accepted. However, Nicholas Copernicus eventually challenged this notion by putting forth the novel theory that Earth is merely another planet orbiting the Sun. Following the introduction of a new theory of gravity by Copernicus, Isaac Newton postulated that all objects with mass are attracted to one another by gravity. According to this theory, the Moon revolves around the Earth, and the Earth orbits the Sun because of their mutual gravitational pull. After around 3 centuries, Newton's gravitational theory was put to rest when Albert Einstein introduced his general theory of relativity in 1915, completely redefining our conception of space and time as well as gravity. According to Einstein, the Sun and other large objects produce a curvature in the 4-dimensional fabric of space-time. Because Earth follows this curve, which we interpret as a gravitational pole, Earth orbits the Sun. The shift from Newtonian gravity to Cernic heliocentrism, from a geocentric model to Einstein's general relativity, emphasizes how scientific knowledge is always changing, even with Einstein's ideas having a strong foundation. Presently, scientists are still challenging, examining, and expanding our knowledge of time in the universe. One major issue arises when Einstein's general relativity, which includes the concept of space-time, meets with quantum physics. The two seem to operate on entirely different rules, and this creates a bit of a problem. Nevertheless, Einstein's space-time theory has held its own for over a century, fending off all challengers. A significant victory for it came in 2015 with the detection of gravitational waves. It is common in science to say that one's opinion is irrelevant to the data. This is particularly true about cutting-edge new instruments, like the James Webb Space Telescope. Thus, just like with the concept of time, it isn't a huge surprise that parts of the JWST results don't match what scientists had anticipated. JWST ultimately challenges science. James Webb Space Telescope has already forced scientists to reevaluate how the early universe once functioned, revealing things that could cause significant changes in our models of the universe during the next 10 or more years of the JWST's existence, from discrepancies in the universe's age to the unexpected brightness of early galaxies. Mike Boylan-Colchin, a theoretical astronomer at the University of Texas at Austin, claimed that the data from the telescope presents a consistent and consistently new image of the early cosmos. Scientists stated that developing fundamental parameters upon which to make their predictions was arguably the most challenging aspect of the process of knowing what the JWST might see. According to astrophysicist and science communicator Neil deGrasse Tyson, the parameters in computer models of the universe are similar to knobs you turn and are used to project outcomes based on theories. Rachel Somerville, a senior research scientist at the Center for Computational Astrophysics at the Flatiron Institute in New York City, gave an example of her work by describing a study she was involved in that attempted to forecast what JWST might observe. Somerville reported that they had adjusted all the variables in their models to reflect the nearby universe, but there was a discrepancy. Their models didn't align with the actual observations. After analyzing the data, Somerville and her team found that accounting for the higher density of the early universe, which was smaller than our current, more expanded cosmos, but had the same amount of mass, would improve the accuracy of their predictions. Other issues were more difficult to fix. For example, several JWST observations showed that the early cosmos was shockingly vivid, with galaxies much larger and brighter than projected by astronomers. Boylan-Colchin noted that no model had predicted the level of activity at that point, implying that everything was happening faster than anyone had thought possible in the early cosmos. According to discussions among experts, the unexpectedly active early universe might be linked to a well-known inconsistency in astrophysics, the age of the universe. Wendy Friedman, a cosmologist at the University of Chicago, pointed out that the Hubble Space Telescope played a crucial role in establishing the scientific consensus on the universe's age, primarily by observing Cepheid stars. These observations led to a measurement of approximately 13.7 billion years, a figure that has remained unchanged. Another method, utilizing the cosmic microwave background, yielded a slightly larger estimation of 13.8 billion years. Despite the seemingly small difference, estimates based on Cepheids can be as low as 12.8 billion years, creating uncertainty. The discovery of luminous early galaxies by the JWST did not resolve this discrepancy. In fact, it prompted Rajendra Gupta, an astrophysicist at the University of Ottawa, to propose an age as ancient as 26.8 billion years, although this suggestion was deemed highly improbable by the panelists. Nonetheless, the variation in the universe's age suggests potential shortcomings in the standard cosmological model and our comprehension of dark matter and dark energy. Wendy Friedman speculated that there might be a fundamental aspect missing from the current understanding. Despite these challenges, advancements in technology such as artificial intelligence and supercomputers, as well as the development of new telescopes like the giant Magellan Telescope in Chile, offer promise in addressing long-standing astronomical questions. Priya Natarajan, a theoretical astrophysicist at Yale University, emphasized the ongoing data revolution, which is expected to greatly enhance models and theoretical understanding in the field. Do you think time doesn't exist and is just a human construct? Tell us in the comments below. Please give this video a thumbs up and subscribe if you haven't already so you can see more videos just like this one.